So I was just going to tell you what I was planning for these lectures. So first of all, there is the sort of aim of the lectures. So what I would like to do is to provide you with some general introduction to the physics of strong electronic correlations. And this will be really very, very basic. It will emphasize materials and the basic reasons why certain materials display what we call strong electronic correlations. So for some of you, it may be a bit too much on the materials science side, let's say, than what you are used to here. But why not? And the second goal of the lectures is to provide an introduction to a technique that has been around for many, many years now and has evolved along the course of time to handle these strong electronic correlations, and that method is called dynamical mean-field theory. It's really a way to think about solids and about solids with strong electronic correlations. So these two parts are fairly introductory, and they cover rather old topics. And hopefully, if I ever get there, in the last lecture, I will get into more recent developments, just a few things. At least at this stage, I'm planning to talk about what we call Hund's metals, and also the question of bad metal and bad metallic transport, just to please Steve. Okay, so concretely, what I'm planning for today's lecture is I was planning to address three things, but very likely I'll only address the first two. Okay. What fraction of your lecture did you succeed in covering? 50%?
Maybe 2/3.
Okay, well, I'll try the same. Okay, 2/3. Okay, 2/3. So the first third would be give you some basic notions about materials with strong electronic correlations. In particular, I want to emphasize the fact that these materials are often multi-orbital materials, and we've heard the word orbitals many times. I want to come back on that. Then I thought that in order to talk about dynamical mean-field theory, it's a good idea that you have clear in your mind what the basic incarnation of Coulomb blockade is in a zero-dimensional system, and the corresponding simple model to describe this, which is the so-called Anderson impurity model. So I'll give you a little crash course into the physics of Anderson impurity model, both in terms of applications to magnetic impurities and to Coulomb blockade in quantum dots. And most likely the lecture of today will stop here. If I ever get there, I will also start introducing dynamical mean-field theory. Okay, so in the first part of the lectures, I would really like to address the following questions. Which materials display strong electronic correlations, while some others don't? And why do we care at all about those materials? Basically, the playground that we're referring to is to a large extent those ones. So we have here in the periodic table the transition metals. These are the 3D transition metals that correspond to gradual filling of the 3D row. But you shouldn't forget there are other transition metals that correspond to filling the 4D row and the 5D row. And in particular, in the last lecture, when I talk about Hund's metal, you will hear a lot about rutenates. Ruthenium is here in the 4D row. Okay? So many of the materials that display strong correlations are materials that contain such transition metals, and I'll explain why in the next slide. Just on a purely phenomenological level, it's completely obvious when you look at the properties of pure elements that, elemental metals, that these are the systems in which electron-electron interactions are important, because I'm sure you know iron and nickel are magnetic. Okay, so, and there is a famous theorem that says that without interactions, there is no magnetism. Okay, so we need interactions to understand the physics of even these elemental metals of the transition metal row. Okay, there are also many materials displaying even stronger forms of electron correlations, which are the materials that contains the so-called rare earth, which are not so rare actually, which correspond to the gradual filling of the 4F shell. So you have these 14 elements here that correspond to the filling of the 4F shell. And similarly, there is the filling of the 5F shell, which are the so-called actinides here. In particular, I may show at some point the phase diagram of plutonium, which is really a strange animal, the strangest of all elemental metals. So why? And of course, this thing is a little bit incomplete. I should also mention that many interesting correlated materials exist when it comes to organic conductors, which is not directly represented here because they are molecular systems. Okay, so why is it that we encounter such strong electronic correlations when we deal with such elements? The reason has to do with very basic quantum mechanics. If you look at the spatial extent of the orbitals that you know from the hydrogen atom, as we move up in the principal quantum number, the s orbitals, for example, as you know very well, have to develop nodes. Okay, so because of that, they have to reach fairly far in the spatial extent. When we look at the d orbital, L equal 2, here is the first time that we have to fill the L equal to d orbital when we reach these elements. And as a result, the radial wave function of these L equal to shell doesn't have to have an E0. So it can stay fairly close because the orthogonality with, you know, lower principal quantum number thing is just ensured by the angular integral. So as a result of that, these wave functions can remain fairly localized around the nuclei, which means that from atom to atom, the overlap between two such wave functions can be fairly small. And it's going to be fairly small in the case of 3D transition metals. It's going to be a little bit bigger or somewhat bigger in the case of 4D transition metals because you have to have one node, and even bigger in the case of in the case of 5D transition metals. By the same token, the radial wave function of 4F rare earth systems, the 4F radial wave function, is extremely localized around the nuclei. And indeed, if you look here, these elemental metals, with the exception of cerium, which has a somewhat more complicated phase diagrams, are metals which have this strange property of having a Curie law for their susceptibility instead of Pauli susceptibility, indicating the presence of a local moment that freely fluctuates despite the fact that they are metallic. So this is an obvious evidence that there is something like a localized electron that carries a spin that you see in a magnetic measurement. Okay, so this sets more or less the playground. The materials that we are talking about are mostly transition metals and their compounds, oxides in particular, but could be other things like sulfides, and rare earth and actinide compounds, and also molecular conductors. The reason is the same, is because the molecules being fairly big, the overlap between the wave functions between two different molecules is small, and hence we have a fairly small transfer integral as compared to some measurement of the screen Coulomb energy on site. So that sort of sets the stage. Okay, so I've already talked about two energy scales that are very important and that dominate at least the high energy physics of all these systems. And one is this overlap between two wave functions centered on neighboring atoms. That would be, in a loose sense, the tunnel amplitude or transfer integrals that will lead to band formation. Okay? And the other one is a typical size of the Coulomb interaction, I should say of the screen Coulomb interaction, on a given atomic site, in a given atomic shell, for example, the 3D shell of my system. And strongly correlated systems are often systems in which these two scales are or at least the bandwidth that derives from this tunnel amplitude, are comparable to one another, and hence can lead to an interesting competition between delocalization of electrons, which is what T wants to do, and localization of electrons because of interactions, which is what U wants to do. Of course, this is oversimplified. As you will see later in this lecture, there is actually other interactions that are very important in the context of multi-orbital systems, and I'll come back to this a little bit later. But the cartoon, if you want, at this stage is the following. That's probably the cartoon that any theorist has of a solid. You know, a bunch of atoms with some atomic shell. The electrons can hop from one atom to the next, but that hopping can be impeded by the on-site U. So that's the cartoon we should have in mind. So it's a story of Mott versus Bloch. Okay? And who is going to win? Okay, so of course the simplest possible incarnation of this competition that plays the role in the field that the Ising model plays in classical StatMech. You know, in classical StatMech, we want to understand, for example, magnetism, symmetry breaking, and we want a microscopic model. To describe that, we write down the Ising model. The Ising model is the simplest model you may want to write. It's very rarely a realistic model, but who cares? It's a good enough toy model that captures the main thing. And the Hubbard model, to a large extent in this field, plays a very, very similar conceptual role than the Ising model. With a little catch, however, which is that people can now realize the Hubbard model in the lab. In the cold atom community, one can realize in the lab a model with a physical system which is fairly close, not to say precisely identical, to the Hubbard model. Okay? So I'm not saying this is an unrealistic model. I'm also among those people who believe that for cuprates, at least many of the very basic and salient physical phenomena, perhaps not everything that Steve described, is already contained in the single-band Hubbard model. But nobody would claim that the single-band Hubbard model is a realistic microscopic description of a real oxide. It has a better chance for cuprates because of the great lifting of orbital degeneracy specific to those materials. I'll come back to this. But for most of the other oxides, this is not a realistic model. But it's a good enough toy model. And let's put it that way, if we can't understand this model that has only one complete constant, U over T, then there is very little chance that we can understand any other. Okay, that was already pointed out by Steve this morning. The physics of this model, well, I guess he didn't talk about the model, but he did mention energy scales at the end, is surprisingly rich and complex. And the reason for this is at a deep level because of the emergence of low energy scales. So we have these two energy scales, U and T, forming a dimensionless coupling, U over T, okay, which are high energy scales. The electronic bandwidth, the electronic Coulomb repulsion, these are scales that are typically, just to fix ideas, in the EV range. So that's what I will call high energy, okay? But when we actually look at the relevant physics, other energy scales emerge, which are much lower by essentially 1 order of magnitude at least than these high energy scales. And one was emphasized this morning. It is the super exchange, which in the strong coupling limits controls the magnetic interaction between localized spins in this model. And that's already much smaller than both U and T. So for the T square over U. So in cuprates, this is something like 1,000 K, while an EV, as you all know, is 12,000 K. Okay? And then if we look more on the metallic sides of things, we may, when we have a metallic state, in the end form some sort of quasi-particles. But these quasi-particles will typically, you'll see that coming in the rest of the lectures, will typically have a coherent scale which can be much, much smaller than the bare hopping amplitude. So you should think in terms of low energy scales that there are at least two that are very relevant. One is the super exchange, and the other one is the quasi-particle coherent scale, whatever it means. We'll see more precise definitions and evidence later, that are the real reason why this problem is difficult. We start from it's not a microscopic model, but already some effective model at high energy. And we need to understand the physics down to low energy scales, typically 100th of these bare energy scales. So fundamentally, this is why it's tough. Okay, but as I said, the Hubbard model, as I showed it a couple of slides ago, is not realistic for many materials. There are actually other degrees of freedom, and hence other energy scales that become important. We may get away with the single band Hubbard model for cuprates for reasons that I'll explain in a minute. But for most of the other oxides, for example, of all these transition metals that I showed to you, there are other degrees of freedom. And these degrees of freedom are, to a large extent, orbital degrees of freedom. And I want to spend a few minutes explaining what those are, because the word orbital was pronounced by many people. Sentil mentioned this in his lectures, also Steve, many other people, I'm sure. And I think you should know a little bit more about those. So you all know about orbitals, of course, in the usual context of the hydrogen atom, right? If we look at the L=2 shell, we have 5 d states, right? And here I formed specific linear combination of the spherical harmonics that are adapted to cubic symmetry, and you'll see why in a minute. I've formed this combination, which are called XY, XZ, and YZ, which, if you open this website here that I recommend, the Orbitron website, you'll see nice plots of these orbitals. So they look like this. You can see here the XY orbital is here in the XY plane, okay? And these two other, x square minus y square, which is nothing else than xy rotated by 45 degrees, and the z square orbital here. And on this slide, I've already decided to split these two things into a triplet and a doublet. There's no reason to do this, of course, if you have complete spherical symmetry. They are all degenerate. But the reason I'm doing this here is because many of the materials we're actually interested in have a specific kind of symmetry, which indeed leads to a lifting of degeneracy in this manner. So, of course, as we go to the solid, we break spherical symmetry, and the environment, the ionic environment of a given atom, is going to break spherical symmetry. Let's look at this specific crystal structure. I think Steve in his lecture already pronounced the infamous word perovskite, but I don't think you showed this picture. So let me show it here. It's a very, very beautiful crystal structure that was discovered in the mid-19th century and actually named in the honor of some Russian mineralogist, the Count Perovsky. And this is how the crystal structure works. It's very, very nice. You have here a cubic lattice of these yellow atoms, and you have another cubic lattice of these red atoms, which are typically the transition metals I'm talking about. And look here, you see that this transition metal is encaged into an octahedral cage built by 6 oxygens. So you have a regular octahedron here. Here I've given you an example where we have perfect cubic symmetry of this perovskite. More than often, this cubic symmetry is actually broken in turn by rotations and tilts of these octahedra, but let's stick to the simplest thing. So we have this perfect cubic lattice of octahedra with a transition metal ion encaged into this cage of 6 oxygens. These cages touch each other by the corners, right, with perfect cubic symmetry. And in the voids here, we put a third atom, which typically can be a rare earth atoms, for example. So I find it less confusing to call it RMO3. O is oxygen, M is the metallic ion, the red guy, and R is a rare earth. And let's pause for a minute on this structure, just so that you understand what it allows chemists and physicists to do. One of the beautiful things with this structure is that it contains 3 atoms. Hence, it leads to the possibility of controlling the valence, the nominal valence of this metallic ion by changing, for example, the chemical nature of this rare earth here. Okay? Oxygen usually likes to take 2 electrons, so it's going to become 2 minus. But depending on the valence of this guy, for example, depending whether it's lanthanum, which will be typically 3 plus, or strontium, which will be typically 2 plus, you can change the nominal valence of the metallic ion. So being a ternary material containing 3 elements, this structure allows to control what's going on the red guy by changing the yellow guy. That's the beautiful thing about this structure from the point of view of doping the system, for example, which in reality means changing the valence of R to affect the valence of M. There are other ways to do that. You can have oxygen deficiency systems or things like this. Okay. So, yes. Please ask questions, of course.
Is there how can I understand what is special about this structure as opposed to another? Or is it just one example?
It's just one of the structures in which oxide most often form. But it's not by no means the only one. There are many other ones. But many, many of the oxides actually do form in this structure. No, it's not a model. No, it's not a model. It's a reality, you know. For example, if we take strontium VO3, in contrast to the Hubbard model, this is not a model. If we take strontium VO3 is exactly in this crystal structure with exact cubic symmetry. Many, many of the AbO3 oxides actually do take this crystal structure with a little twist, which is that these guys would rotate a little bit and tilt a little bit, hence lifting weakly or more strongly the cubic crystal symmetry. Okay? So that's really what many oxides do.
What is it, charge dependent?
Sorry?
Is it charge dependent?
Whether there are rotations and tilts?
Yeah.
Good question. Actually, it all depends on how close to close packing you can reach. Okay? And as you move along the rare earth series, the ionic radius of the rare earth actually goes down. Can somebody explain this to me? Why is that true? It's a little bit counterintuitive, no? You increase the number of electrons.
Because it's more close to nucleus.
Yeah, this guy knows everything. So you increase the nuclear charge, Z, and hence the electrons get pulled in more strongly, and hence the ionic radius goes down. As we go to smaller and smaller rare earth, we have more room for these guys to actually tilt and rotate. And so when you have a big rare earth, like strontium or lanthanum, this guy actually likes to be close to cubic. But when we move to heavier rare earth, actually typically these things tilt and rotate. And that's another control parameter of these structures, besides the doping.
So is the fine rigidity of the structure?
Well, I mean, it's a compromise between electrostatics and, bond formation. Okay. So let's go back to the pure cubic, and let's look at what happens when we have one 5-fold degenerate d orbital subject to the cubic symmetry breaking of this perfect octahedral environment. Well, that's a problem which is called crystal field theory, This is something that Hans Bethe worked on in the 30s, for example. And what happens is that the 5-fold degenerate symmetry of the d orbital is lifted into a 3-fold degenerate triplet, which is made of the x, y, x, z, and y, z, and a 2-fold degenerate doublet, which is made of the x square minus y square and z square orbitals. And it turns out that in this octahedral environment, the T2G triplet has lower energy than the EG, the so-called EG doublet. And the reason for this is extremely easy to understand. If you look at an x square minus y square orbital, which has this shape, the lobes point directly to the lobes of the p orbitals of oxygen. Hence, there is a very strong repulsion which disfavors these two orbitals, right? While for the 3 orbitals in the T2G state, the lobes point in this manner. So that's more like pi bonding. And hence, as compared to this situation, these orbitals are favored. So this is why in an octahedral environment, the T2G states are lower in energy than the EG states. Of course, if you change the environment, if you go from octahedral to tetrahedral, something else will happen. In fact, in tetrahedral environment, these two guys have lower energy than these guys. Okay, so in terms of group theory, we've just looked at how now the irreducible, what are the irreducible representation of the cubic symmetry group. That's what we are really doing. Okay, so what I said here is that in the free atom, we have perfect 5-fold degeneracy. This is 10 here because there is spin, okay, in this diagram. If we have a cubic symmetry with octahedral environment, it splits into a T2G triplet and an EG doublet. And if we keep on breaking the symmetry, like if we go to tetragonal symmetry, this T2G will split and this EG will split. And this diagram already allows you to understand why in cuprates a one-band Hubbard model is not such a bad idea. Perhaps the reason is that these orbitals in cuprates, let's take a tetragonal cuprates, like mercury-based single-layer cuprates, which are tetragonal, just to make our life simple. None of the 3 compounds that Steve mentioned are actually tetragonal, but there are some tetragonal cuprates, so that's nice. So let's focus on that. So copper in the parent compound of cuprates is D9, has 9 electrons. And so you can happily put 6 electrons in these guys, okay? You can happily put 2 electrons in this guy. And then you are left with this guy here, which has only 1 electron. And it turns out that in cuprates, the octahedron I'm talking about is so distorted, that's the Jahn-Teller distortion that Steve was talking about, that this guy really lives way above all the others. So all these guys are essentially vegetables. They are filled, completely filled, and do nothing, while this guy stands at the top and is occupied by 1 electron. Hence, it's not a bad idea to think that perhaps you can get away with a single band, meaning a single orbital model, which is nominally half-filled for the parent compound. That's how it works. You can ask the following question. Is there any other oxide in which we have essentially a single band half-filled by 1 electron? And the answer to this question is, with a few remarkable exceptions that I don't have the time to discuss right now, the answer is no. For all the other hundreds or thousands of oxides known to mankind, actually this orbital structure does matter, and we have partially filled shells with certain number of electrons in all these guys. So the one-band description applies especially well to cuprates, but is not likely to apply to all, essentially all, with exceptions, like the iridates for subtle reasons. to essentially all the oxides that we know. Andre.
And just in terms of numbers, what's the energy equation?
Okay, so in cuprates, this is several EV, right? This would be many EVs. This is maybe what? Certainly, this is below the P levels, so this is also several EVs. So this is maybe 10 EV, and this is maybe 7 or 6 or something like this. It's in cuprates, it's a large number. You'll see for other oxides numbers in the following. Yeah.
What about the electrons of the oxygen?
Ah, good question. So, of course, this is a crystal field diagram that takes into account the electrostatic energy of the oxygens. But this guy hybridizes with the neighboring oxygen orbitals. So when I said one band, what I really mean is that there is a combination, which is here the antibonding combination between x squared minus y squared and px and py, which form one band at cross Fermi level. Okay? Whether we should also include the px and py in the low energy description, those guys are only 1 or let's say 2 eV below that band, okay, has been the subject of heated debates in the cuprate community. And I don't want to discuss this now. Okay. It's one band in this simple quantum chemistry sense that the antibonding hybridized band between x squared minus y squared and px and py is the only band crossing Fermi level in the cuprates. Nobody disputes that. And it's also a remarkable exception in the land of oxides. Okay, more questions about this? Okay. So, by the way, I mean, you know, the manifestation of crystal field theory is something that you see perhaps not every day, but very frequently. This is one, for example. The reason why ruby is red is because the D states of chromium 3+, which are the impurities that are there to give the red color in some aluminate matrix, this crystal field splitting between T2Gs and EGs turns out to be more or less 2.1 EV, which is just enough to absorb everything except red color. Okay? So this is a manifestation of crystal field theory. Okay, very good. So I've talked about basic orbitals and the way they overlap and so on, and I haven't told you anything about interactions, except that there is a Hubbard U. But you can easily imagine now that because there are other orbitals, there are also other interactions. So there is more in multi-orbital systems than just a Hubbard U, and hopefully, if I ever get there, in the third lecture, you will see manifestations of another coupling, which is the Hund's coupling J, that I'm going to mention in a minute, that play a big role in inducing electronic correlations in routenates, we think. Okay, so what I want you to realize is that an isolated atom, even an isolated atom, is not just filling with electrons the 1 electron level of a hydrogen atom. There are electron-electron interactions. So an isolated atom is a small, well, actually not so small in terms of size of Hilbert space, but it is, as compared to the infinite volume Hubbard model, it's still small. It's a small many-body problem. And we need to think about the eigenstates of this many-body problem. That's what we call the multiplets of a given atom or atomic shell. So let me show you how it works. Just focusing for simplicity on a threefold T2G shell, because the full classification, even just for the fivefold shell, is somewhat complicated. I flash a couple of slides that are very relevant here in the context of the Hebrew University of Jerusalem. You'll see why. But let me first, just for pedagogy, focus on a threefold T2G shell. So in that case, we have these cubic harmonics, xy, xz, and yz. They can be chosen to be real. And you can see that there are only 3 coupling constants. So there is the Hubbard U. What is the Hubbard U? It's basically the energy you have to pay to put 2 electrons with antiparallel spin in the same m orbital, let's say xy. So it will be something like this. The matrix element in these 2 orbitals, in the same orbital, okay, of some Coulomb interaction, which to be anywhere close to what is reasonable for, say, an effective T2G low energy model, should be a screened Coulomb interaction. So what you should do if you are really interested in evaluating this is street screening from all the other bands in some way, for example, RPA, calculate the screened Coulomb interaction, and take matrix elements of this guy within this orbital. That would be your Hubbard U. And in typical oxides, a typical value of this runs anywhere between 3 eV and 7 or 8 or 10 eV, something like this. Okay. So now we can do something else. We can take 2 electrons with in 2 different orbitals, right? And that will define a different integral, which is, for example, here taking the xy wave function and here taking the yz wave function. And obviously, because the overlap of these 2 wave functions is smaller, this u prime is going to be smaller than u. But that's a different coupling constant. And of course, there is exchange, because we do quantum mechanics. There is the exchange integral. Here, in the case of T2G, there is only 1. So this is the exchange integral J, which is here. Please observe here that we have here mm prime and here mm prime. And once you do all this, you can write the effective Hamiltonian that describes interaction in a T2G shell according to various symmetry principles dictated by cubic symmetry. And what happens is that you have these 3 coupling constants that multiply these various terms. There is the term for putting 2 electrons with antiparallel spins in the same orbital, putting 2 electrons with antiparallel spins in different orbitals. That's the u prime. And importantly, there is a term here for putting 2 electrons with parallel spins. Observe here that we have sigma sigma with different orbitals. And this guy is u prime minus j. So this is the smallest of all coupling constants. And this thing expresses the well-known Hund's rule, that when you start filling up a shell, it is actually more favorable to put a new electron with parallel spin into an orbital that is not already filled. So it's like when you fill in the double seats in a bus, okay, you start filling first the seats in a singly occupied manner. So everybody has 2 seats, and then only for more than half-filled shell, some poor guy has to sit next to another guy, okay?
And then if you want to put more in, they have to go head down.
Yeah, and they have to go head down. That's right.
Form of that term u prime minus j require the symmetry of cubic symmetry that you can rotate among.
So that takes into account cubic symmetry, and this is why actually there are these terms, okay, which are not density-density terms. But please observe that we still have 3 coupling constants only, and at this point I haven't said anything about how u prime should be perhaps related to u and j. So we can rewrite this Hamiltonian in terms of the generators of the symmetry, and we have basically we have a symmetry which is u1 total charge times su2 spin times SO3 orbital, right? And we have the Casimir of each of these symmetry, S square, L square, and N. And you can trust me that when you actually rewrite this Hamiltonian in terms of these Casimirs, you get the following expression. And you see that this comes, the spin square comes with the 2j, and the L square, which is the effective angular momentum rotating between the 3 xy, yz, xz orbital, comes with a j over 2. So that expresses very nicely the Hund's rules. The Hund's rule says that you should first maximize spin, then maximize L. Okay, so this is writing the Hamiltonian in terms of these three symmetry operators, and when you expand all these things, this is an exercise you can do. Don't ask me to do it on the board at the tutorial, okay? I'm not going to do that, but you can do that, and you'll get this. If you furthermore impose that, oops, sorry, somebody should have complained. Yeah, U prime is gone. What happened? God. Okay, so there is something I didn't tell you between this slide and this slide. Something has happened. If you furthermore assume that the Coulomb screen potential has almost spherical symmetry, which for very localized orbital may not be such a bad approximation, then you can show that this U prime is actually related to U and J by U prime equal U minus 2J. But that assumes spherical symmetry of the Coulomb screen interaction. So that's an additional approximation, okay? And if you do that, you get this. Yes?
So basically when you write down these matrix elements, you can perform some rotation.
Yes.
And then to transfer one matrix element
Yes.
to the combination of the others, right?
Exactly. And the hero of this field, well, one of the heroes of this field, and that comes, well, I'll come back to this, is actually Mr. Giulio Rocca. And I think it's very proper in this set of lectures to give tribute to Rocca, who was one of the eminent founder of physics here at the Hebrew University of Jerusalem. Giulio Rocca actually has classified, in the case of spherical symmetry, all the multiplet structure of many body atoms using group theory methods. And he started that in 1941 when he emigrated to Israel, fleeing the anti-Jews measures in Italy. He's an Italian Jew. And he started his first paper at the Hebrew University of Jerusalem, Palestine. You see, published or received November 14, 1941. And this was a fairly complex set of papers. I invite you to take a look. I'm not saying reading those because they are really tough. Okay? But the fourth paper was published in 1949 at the Hebrew University of Jerusalem, Israel. It's a very moving story, I think, that when dramatic things were happening in Europe at that time and all over the world, Giulio Rocca was spiritually resisting what was going on by doing such things. I think this is really a very beautiful story. Okay, Giulio Rocca, by the way, after doing all this beautiful group theory, was also one of the physicists who believed in computational physics very early on. Okay, so I'm not going to tell you much more about these complicated integrals. If you have more than a T2G shell, you should just know that the matrix element of the Coulomb interaction in terms of all these orbitals can be classified by group theory methods, and this is due to Rocca and Slater with equivalent results and somewhat different notations. These things exist in textbook. If you want to know what the Rocca-Slater integrals are, you can just go there. Okay, so, yeah, 45 minutes. This was the interactions. Now, what I want to tell you a little bit more is why we're interested in such systems.
Can I ask
And yes.
Some people in this field introduce two J's. One is called J and other J prime.
Yes.
Can you comment quickly on that?
Yes. Well, I mean, I think it is correct that in the case of a T2G shell with cubic symmetry, there is no such thing as J and J prime. But let me cross-check that for you. In the case of the full five-fold orbital, there are certainly several different exchange integrals. And they are all encoded into this U, M1, M2, M3, M4. Okay, so let me give you some general idea about why we care about such materials, and that will be just more like a few phase diagrams and things to just whet your appetite. Okay, so one of the really interesting things about these materials is because the electrons are such strongly interconnected one to the other through these narrow bandwidth and strong interactions, collective phenomena take place. And I've mentioned already one, which is magnetism. We've heard about high TC superconductivity earlier. One of the prominent things that happen in basically all of these materials is this competition between itinerancy due to the hopping, okay, and localization due to U and other interactions. So not surprisingly, some materials, not perhaps the majority of them, but some of these materials are poised close to the metal-insulator transition where these two things can really compete. And let me give you some examples. This is one example, time-ordered one, which was studied a lot in Bell Labs in the 70s, in France as well. That's vanadium sesquioxide. And this guy, as a function of temperature and, for example, pressure or substitution of vanadium by something else, sometimes called chemical pressure, has the following phase diagram. And you already see a fairly complex phase diagram here. If you look at high enough temperature in this range, above 170 K or so, what you see is that at low pressure, the system is an insulator. It's an insulator with local moments present, has some Curie-Weiss susceptibility. And then as you increase pressure, this insulator can be metallized through a transition here, which is a first-order transition, without a change of lattice symmetry, but with a change in the lattice spacing. And that first-order transition line ends here at some critical endpoint, which is a second-order critical endpoint. There is no symmetry distinction at finite temperature between a metal and an insulator. So it's a bit like a liquid-gas transition. You can go around this critical endpoint. So this is a metallic state, which, however, displays signs of strong correlations that I may come back on later. This is an insulating state without magnetic order. I insist on this. And then this state has, of course, fluctuating local moments. Something must happen to beat this entropy as you lower temperature, and what happens is ordering. So this insulator orders into an antiferromagnetic insulator here, and you see here three phases: a paramagnetic insulator, a paramagnetic metal, and an antiferromagnetic insulator. This is not a unique phase diagram. You see a similar phase diagram in the case of the BDT organics that were already mentioned in a few talks by Senthil in particular. Here you see temperature, pressure, and here you see a first-order transition line between an insulator and a metal, and in this case an antiferromagnet and even a superconductor in proximity to this antiferromagnetic phase. So of course this is very nice because you can control this metal-insulator transition by various external parameters like pressure or strain or, of course, doping. And it can even be useful for something. This is a closely related oxide, vanadium dioxide. I just finish this and answer your question if I can, in which this metal insulator transition turns out to be very close to room temperature. So that's actually useful in order, for example, to coat windows. You can have at high temperature a metallic state that reflects infrared, and at low temperature an insulating state that lets infrared come in your room, okay? And if you can coat your window with a thin enough layer so that it's transparent, and you can tune the metal insulator transition to be around 20 Celsius, then you have something which people quote an intelligent window. Well, it's not so intelligent, just switches between two states, you know, that decides to reflect infrared when it's warm outside and let it in when it's hot outside, when it's cold outside.
Yeah, to the previous phase diagram.
Yes.
So assume, considering the paramagnetic metal state goes into an antiferromagnetic transition. So what do you understand?
Here?
Yeah.
Yeah. So, well, the super exchange is still active there, and you have a, it's actually a first order transition.
But so the metal insulator phase boundary is really, you decrease temperature doing that, and then it's
Yeah, it's preempted by the magnetism. So you can't, in this system, follow, that would be wonderful, follow that phase transition here down to low temperature. You're really always preempted by magnetism.
But I should think
It's
of
a-
that line also as a metal insulator.
Yeah, sure. This is also a metal insulator. So this is a transition at which simultaneously you have appearance of magnetism and of a gap.
Is there a cell
The,
that there's no
the reason is entropy, is because this metallic state, you have to ask, what is the coherent scale of quasi-particles here close to the transition? That would be the scale at which you cross over from having at high temperature log 2 entropy and at low temperature linear in temperature entropy like you should have in a metal. And it turns out that this scale is so low that you have an entropy that can be quenched by J before you reach really coherent quasi-particles. That's the reason why magnetism intervenes in this system.
And what are the orders of those?
I think they're all first order.
And is there absolutely certain that there's no antiparamagnetic metal?
No, there is actually. If you do oxygen deficient compounds, that was discovered by Rosenbaum, Tom Rosenbaum, many years ago, there is actually here a little pocket of metallic antiferromagnetism. Okay, well, I'm not going to reach 2/3, so I'd better hurry up a little bit. Okay, so there are many other examples of such metal insulator transition. Let me mention one family which is really interesting, which is the rare earth nickelates, which have quite different physics from the previous one, but in which there is also a metal insulator transition, which can be remarkably controlled by changing the rare earth in these materials, and can be controlled by many other means. I obviously don't have too much time to review all this. Okay, there is one thing I want to mention here, because this will come up in the rest of these lectures, which is that there are common aspects which are signatures of strong correlations in these systems. And one of these signatures, something we see very often, and that will come back in the rest of the lectures, is very large transfers of spectral weight when we vary some external parameter, for example, temperature, over even a modest range. So let me take here the example of the optical conductivity of one of these nickel oxides, actually neodymium nickel oxide, and look at what happens here. So obviously these are this is the metallic state. We have some Drude peak here, and this is the insulating state with a gap. But look at what happens here when we actually change temperature in the metallic state by just perhaps 100 Kelvin. Okay, so what you see is that as you heat up the system, there is a very rapid drop in the Drude peak and a corresponding transfer of spectral weight to very high energy, up to 1 eV, which is an energy scale which has nothing to do with the range over which you vary temperature, which is 2 orders of magnitude larger. So you have these huge transfers of spectral weight between low energy things that perhaps can be described in terms of quasi-particles and high energy things reaching up to the scale of the bandwidth or Hubbard-U. Okay, so the low energy and the high energy talk to each other through these transfers of spectral weight. That's something you have to keep in mind, which is really important. Okay, I don't want to tell you much more about materials. Maybe we can keep some of these slides for the discussion session tomorrow. I was going to tell you a little bit more about F-electron materials. Let me just point out one thing, which is that if we now look at the phase diagram of actinides, this is sort of a quote-unquote phase diagram which displays the phase of the monoatomic metallic actinides as a function of element. And you see here that there is, in particular near plutonium, an incredibly complex phase diagram. Metallic plutonium, just monoatomic metal, has 1, 2, 3, 4, 5, 6, 7 different phases as a function of temperature. And this is also a manifestation of the competition between mode localization of F electron and delocalization. But I don't want to emphasize this too much. Steve also talked about high TC superconductivity. This is another high TC superconductor by all standards. You know, this is the two-dimensional organics. I already showed this phase diagram. Senthil mentioned these systems. And you see here that this material has a TC of about 14 Kelvin, something like this. But if you compare this 14 Kelvin to the bandwidth of this molecular metal, which is fairly small, then this is also, I think, something that should be called a high TC superconductor. So high TC superconductivity is another of these big things that strongly correlated materials do, and the reason why we are interested in those. Okay, so you will be welcome to ask more questions in the session tomorrow, end of the day. The summary of this, what was supposed to be the first third of my first lecture, is that these systems have many degrees of freedom, charge, spin, orbitals, and also lattice, which I didn't talk about at all. Up to now, many competing phases. These phases have small energy differences, and that actually this leads to many different handles to control these phases. And all the complexity is due to the fact that there are small emerging energy scales. Okay, so this essentially concludes this very introductory part. There is one thing I want still to emphasize, which is that the key to success in this field is to have a magic triangle of activities, which entirely relies, I don't know how to display a triangle that doesn't look unstable and that relies on one thing only, but that's what this is supposed to mean. You know, this is a solid base, which is the elaboration of materials. This field does not exist without chemists and physicists growing samples. So this is really the core of the activity, and it is the core activity from which all the science can be done. Hence, I mean, the Moore Foundation, for example, has understood this absolutely beautifully by funding the material scientists first in their endeavor, and I think that's very smart. And then, of course, experiments. Steve emphasized how the field of ITC cuprates, if anything, has allowed several experimental techniques to be pushed to the edge and improved considerably, like RTSS-STM, and this is an important thing to remember. And also sometimes theory is sort of useful. Yeah. So what we can ask of theory is several things. Of course, understanding basic physical mechanisms and constructing effective low energy theory. I'm also a theoretical physicist. I believe in effective low energy theories. But my point of view is that this is not quite enough, and that it's also very valuable to develop quantitative theoretical methods, including computational ones, that can come to grasp with the models and hopefully even more realistic models of the materials we are interested in by matching low energy and high energy. And beautiful things happen when you're really able to match these two worlds, to have quantitative theoretical methods that can go at the quantitative aspects of systems and go from high to low energy and match with the effective low energy theory understanding of things. So one theoretical agenda that I really like in this field is to push simultaneously this and hopefully have these two approaches talk to one another. Okay, so now that you've seen this very broad introduction, and if you have questions, it's a good going to ask. Okay, I want to go to something which is a lot more basic. Which I could call Coulomb blockade in a nutshell. So I asked myself, what is the simplest model in which we can illustrate in a concrete manner this competition between Coulomb blockade, between the blockade of charge motion by U, okay, and the possibility of forming quasi-particles or having electrons moving around effectively at low energy due to hopping. And the simplest context in which you can describe that is by studying a little zero-dimensional system in which there is a big U acting on it. So that's what I'm going to do in the last half hour of the lecture. Okay. So it's literally correlation effects in a nutshell. Okay, we are just looking at a nutshell on which U will act. Okay, so let me start just with a simple Hamiltonian. So previously you had a Goto full complex Hamiltonian. Let's now look at the simplest possible one, which is the Hubbard model in which I remove the hopping. So I just have one site, because all sites are disconnected. I can as well consider one site. And this site has a non-site U and just an energy level. So it is the simplest possible atom, right? We have one atomic level, epsilon d, and we have an interaction when this level is populated by two electrons with opposite spins, and the Hilbert space is 4 states, right? So everybody can solve this, especially because it's already diagonalized for you here on the board, right? So we have 4 states. The empty states, energy 0. The singly occupied state, which is doubly degenerate, and that's very important for the following, which has energy epsilon d. No magnetic field. I didn't put a magnetic field here, which would split these two guys. And the doubly occupied state, which has energy 2 epsilon d plus u, obviously. Okay, so we've solved this many-body sort of single atom system. And we can ask, for example, what about occupancy of the shell? Well, we can easily just do simple StatMech, work out the occupancy at finite temperature. And what you will see is that at 0 temperature, if epsilon d is smaller than minus u, then the level is so deep that you want to have 2 electrons on it. Then there is a level crossing at epsilon d equal minus u, as you can see from here, comparing these two energy levels, in which you're going to have a doubly degenerate state with 1 electron as ground state. And then for epsilon d positive, the ground state is empty. So, of course, these two regimes here and here are not very interesting. The really interesting regimes is this regime in which you have a doubly degenerate ground state, and also possibly these regimes here, which correspond to an extra level crossing between the single occupied ground state and either doubly or empty levels. Okay, in the jargon of this field, this is called the local moment regime. Why local moment? Because we have a spin up or a spin down. And this is called the mixed valence. Why mixed valence? Because the valence of your atom here fluctuates between 0 and 1, and here between 1 and 2. Okay, we can also do spectroscopy. Yes?
So this is epsilon p minus mu.
No, there is no mu here. There is no mu. There is just this. This is just an atom. There is no mu. If you want, it's epsilon d minus mu. It's your choice. But it's just an atom, a d level and a u. That's all. If you want to tell me that there is a reservoir.
Electrons is not fixed in your ensemble. So
Here is fixed.
but you have the mixed valence.
No. Here I'm just describing the ground state. Epsilon d positive, ground state is 0, right? Epsilon d between 0 and minus u, ground state is up or down, doubly degenerate. And this thing here is just temperature smoothing. You know, you just have an ensemble of these guys, right? And you just calculate the average N. That's all. If there is no reservoir here, just a collection, just an independent collection of N atoms. That's all. And if it's finite temperature, you know, you have thermal fluctuations in the number. But you're right. I mean, when I'm going to couple a reservoir, epsilon d will be epsilon d minus mu. That's true. Okay. So I can also do spectroscopy of this atom, you know, like people would measure in photoemission spectroscopy. So I can introduce this object, which is the spectral function that you'll hear about in all my lectures, which is the following thing. I take the ground state, I add an electron, and I look at the overlap with all the possible excited states of this system. And I look at this overlap in an energy resolved way, right? Or I do the same thing by removing an electron. And in the local, I can generalize that to finite temperature. In the local moment regime, we have two atomic transitions, one which corresponds to removing an electron, and one which corresponds to adding an electron. And the transitions, the corresponding transition is epsilon d minus 0, which is epsilon d. And here 2 epsilon d plus u minus epsilon d, which is epsilon d plus u. Okay? So this is the spectroscopy of this stupid single level atom. Okay. So now things become more interesting when I decide to couple this single level atom to a reservoir of electrons. So what am I going to have? I'm going to have my atomic Hamiltonian. It's going to be coupled to a reservoir of electrons, which is, say, just a band, and I'm not going to be very specific about this epsilon k, just free electrons reservoir. And they will be coupled by single electron hopping from the bath to the atom or from the atom to the bath, with a certain amplitude Vk that can depend on momentum. So this model, the addition of these three terms, is called the Anderson model, the single impurity Anderson model. And you should really view it as an atom in a bath. Okay. And it has relevance to several different physical systems. Historically, it was introduced in the 60s to describe magnetic impurities in metals. So the idea is that you have a conduction electron C, and you add one, for example, transition metal, and you envision the possibility of an electron from the conduction electron to going to your transition metal shell. So for example, classic example is manganese in copper, for example. And there are many other examples. Of course, this model actually elaborates on earlier ideas, which are the ideas of Friedel in particular, who didn't worry too much about the interaction here, but invented the concept of the broadening of this atomic level by the coupling to the bath. And this is what he called the virtual bound state concept. Okay, in the 90s, this was given a new twist by considering what we could call artificial atoms, and this is a subject which has been very popular in Israel also, which is the possibility of elaborating little droplets of a two-dimensional electron gas, for example, in a MOSFET, in which now you should view this little island here as being my artificial atom. So, of course, typically it will have many atomic levels, but if the energy spacing is large enough, you may want to focus only on one. And you can inject electrons into these islands or remove electrons out of these islands by coupling these two reservoirs, which are here and here, and controlling through these gates here, the left and the right gate, the amplitude of these V case. So this would be the turning amplitude between the reservoir and the dot. So the letter D here comes very handy because it can be the D shell of manganese or it can be the electron on the dot. Okay, just a fortunate coincidence. Okay, of course, in this case, we have two reservoirs. If we want to measure transmission conductance, we need two reservoirs. So it's a little bit of a twist on the Anderson model in which instead of one bath, we have two baths, a left bath and a right bath. But fundamentally, doesn't change too much the problem. Okay, one thing you may want to be interested in, for example, in the context of quantum dot, is the conductance through this system. And this problem was addressed by several people in the early 90s, and there is a beautiful formula which is due to Yigal Meir and Ned Wingreen, which relates the conductance from the left to the right reservoir, subject to a very small DC bias, to the spectral function of the electron on the dot. So this single electron spectral function that I introduced before as a spectroscopic probe turns out to be also the transmission coefficient of my device in the Landauer sense. And you should pause a little bit and look at this formula, which is very remarkable because it looks like a Landauer formula, right? Integral over energy of some difference in Fermi functions times some transmission coefficient, but it's really a Landauer formula which applies to an interacting system. So it's one of these cases in which one can derive a Landauer formula for an interacting system. It's a very nice example. But it also tells you that if you're able to say something about the single electron spectral function, you're going to be able to say something about the conductance through the dot, which is not such a trivial statement in the end. Okay, so let me look into the high temperature regime. The aim of this is to gradually take you through the physics of the Anderson impurity model for this example. So let me first look at the high temperature regime. I should have introduced before a very important quantity, which is the width of the virtual bound state. And can you see if I write here, sort of? Okay. So the width gamma of my atomic level, which is now coupled to a reservoir, will be given, obviously, by the Fermi golden rule. So it's going to be pi times the transition matrix element squared, V squared. If I have two reservoirs, there is a left and a right one, okay, times the density of states, say, at the Fermi level or wherever in my reservoir. Okay? So that would be the way the level is broadened when it's coupled to the reservoir, or you can also think about it as the typical inverse time scale that an electron spends on the level before being kicked out to the reservoir, or the opposite. Okay, so if I look at temperature which are much higher than this scale, I can happily take my single atom spectral function, or at least you could think you could do that, and inject it into this formula to deduce the conductance through this dot. And what you're going to get is this. The physics of this is very simple. Each time there is a degeneracy between two levels with different charges, say 0 and 1, it becomes very easy to have an electron transferred from the reservoir to the dot, and so the conductance will have a peak. So there is a peak here at epsilon d and a peak at epsilon d plus q. In between here, in the local moment regime, the charge is blocked because it costs a finite energy gap to have a charge fluctuation. Okay? So this is called Coulomb blockade. Oops. Coulomb blockade, suppression of the transmission conductance due to the blocking of charge because of U. Okay. If we decrease temperature and you trust this formula, what should happen, of course, is that as you decrease temperature, you make this Coulomb blockade stronger and stronger in some way, because the gap becomes more and more visible. Okay. So all this is nice, but, and it works in practice, but it's also fundamentally wrong. And the reason it's fundamentally wrong is what we've done here is to consider the transmission through the dot by using, for the spectroscopy of the system, the V equals 0 case. So we've taken the spectral function of the isolated atom, plugged it into this formula, and deduced something about Coulomb blockade. But actually, you should be very careful that, in fact, this V equals 0 limit is a highly singular limit. And what you should really do is turn a small v, understand what happens to the whole many-body problem, and then address the question of transmission through my dot. So this is something that was realized in this context in two beautiful papers in the 80s, Glassman and Reich and Patrick Lee and Mr. Ng, who actually pointed out that you should really solve first the many-body problem of the dot coupled to the leads to understand this transmission problem. So let me take you to this conclusion by considering the simplest next toy model that you may want to understand. And this is the case because we find a full extensive bath too complicated. Let's imagine that my bath in turn only contains one electronic state. Okay? So now what is the dimension of the Hilbert space? Can somebody tell me? Okay, bets are open. 8? Wrong answer.
16.
Sorry. 16. Yes, thank you. So we have a 16-fold Hilbert space, 4 times 4. Okay? And here you see there is no k, so just one value of k, and just hopping to a single level also in the bath. So diagonalizing a 16 by 16 matrix is a pain, but fortunately I can use symmetries. So I have two symmetries, at least. One is the total charge over the both sides, and the other one is total spin, so I can split this 16-fold Hilbert space into 0, 1, 2, 2, 3, and 4. Okay? And the biggest block you have to diagonalize ever is 3 by 3, which everybody can do in this room. Okay. So in fact, let me focus on this regime, which is the most interesting. Well, I have, say, 1 electron on the dot and 1 electron in the bath, or perhaps 2 on the dot and 0 in the bath. So the state with 2 electrons overall. There are 6 such states, but it splits into a sector with spin 1 and a sector with spin 0. There are 3 states with spin 1, obviously, but there are also 3 states with spin 0 because they come from the states that have 2 electrons in the reservoir, 0 on the dot, 1, 1, and 0, 2. Okay? So what happens when you turn on V in this system? Well, in the triplet state, nothing happens. Why is that? Because if you are in the triplet state, let's take this one, this component of the triplet state, you just cannot hop because of the Pauli principle. So the effect of V in the triplet sector is null. There is no effect. However, in the singlet sector, something happens, which is, of course, that you can couple to a virtual high energy excitation, which would be the doubly occupied state on the dot, and hence the wave function becomes a superposition between becomes this superposition, if you want, between a state which is forming a singlet with 1 electron on the dot and 1 electron in the reservoir, and these states which are doubly occupied on the dot or doubly occupied in the reservoir. And when you turn on perturbation theory in V, the wave function becomes this state with a big coefficient plus that doubly occupied virtual state with a small coefficient. Okay? So because of this mixing, the energy of the lowest energy singlet sector state becomes lower than that of the triplet by an amount which is, of course, V square over U. And this V square over U is nothing else than the super exchange also that it's the same sort of argument. So the point is that the ground state of this system with non-zero V is now no longer doubly degenerate. Immediately for infinitesimal V, the ground state becomes singly degenerate. It is a singlet, which is basically this state. Dominantly, it is screening the spin on the dot by a spin in the reservoir, but with a small admixture of states that have a double occupancy on the dot or a double occupancy in the reservoir. And you can't have the physics of this screening without having the admixture to these other states. So what does that mean? That means that you have included now in your ground state wave function states in which the charge on the dot is no longer 1, but can be 0 or 2. And the minute you have that in the wave function, it becomes very easy to transmit an electron through the device, because these charge fluctuating states are already there in your ground state wave function. So the consequence of this, without doing any other calculation, is that what should really happen is that maximum transmission conductance is restored in the local moment regime to its maximal possible value, 2e squared over h. So instead of having this story here with the Coulomb blockade gradually developing as we go to t equal to 0, what we should really have is complete suppression of the Coulomb blockade all the way to maximal conductance 2e squared over h as we lower temperature. Completely opposite prediction. Okay. So is that seen experimentally? And the answer to that question is yes. This was seen experimentally in the late 90s, about 10 years after this prediction, in particular by the group of David Goldhaber-Gordon, then at Harvard, I think. Is that MIT? Okay, sorry. Next door. And also Leo Kuvenhoven co-workers. Yeah, he was a junior fellow. Well, let's not get that fight started. Okay, somewhere there. And that was the first signal. Okay. Is that all? Okay, so here is the first signal. You see that this is the conductance in the so-called Coulomb blockade valley at 400 milli-K. You just go down to 90 milli-K and look at what happens. The conductance increases, which is what you want to see from this many-body effect. Of course, this is not quite full saturation. This was reached later, where you see here full restoration of the Coulomb, full killing of the Coulomb blockade to essentially 2e squared over h. But I want to go back to this formula here, which is still valid. We didn't make any mistake in deriving this formula, provided, I have to stop soon, provided this has to be the spectral function of my dot with V taken into account from the start. So what does that mean? This means, if you look at this formula in this way, that something must happen at low frequency in this spectral function to allow G to reach 2e squared over h. So the story cannot be that we just have, where is my spectroscopy of this stupid dot? The story cannot be just that the spectral function will be too broad and peak here. there has to be something emerging here which allows to restore conductance to its maximal value. So something must emerge here at omega equal to 0. And that's the so-called Abrikosov-Soule resonance that I'm afraid I will have to address tomorrow only. Let me see. What else do I want to tell you? Yes, maybe I'll just stop here. And on the menu for the next lecture, we'll be finishing and continuing this story so that you get fully familiar with the physics of, say, the Anderson impurity model of an atom coupled to an environment. And then this is the building block to understand what dynamical mean field theory is about that I'll do also in the next lecture.